A spacecraft can fly closer to the sun than anything humans have ever built, while the instruments behind its shield remain at roughly room temperature. The side facing the sun takes heat that could melt steel. A few inches behind it, the electronics keep working as if they were sitting inside a house. The space between those two temperatures is almost nothing. And that same physical trick is the reason sunlight feels gentle on Earth, instead of turning every afternoon into a disaster. The spacecraft is called Parker Solar Probe. In June 2026, it completed its 28th close pass by the Sun, once again coming within about 3.8 million miles of the solar surface. That sounds like a long distance until you remember that Earth sits about 93 million miles away. Parker does not merely look at the Sun from a safe seat. It dives through the outer solar atmosphere at about 430,000 miles per hour, faster than anything humans have ever built. At that speed, it could cover the distance from Philadelphia to Washington in about 1 second. This is useful information if you are late for a meeting, although arriving inside a carbon heat shield might create new problems. The front of Parker faces temperatures near 2,500 degrees Fahrenheit. Behind the shield, many of the instruments remain around 85 degrees, not 850, about 85. A warm day in Maryland. The shield is only about 4.5 inches thick. It does not contain a giant refrigerator. It does not create a bubble of winter around the spacecraft. It simply prevents most of the solar radiation from reaching the equipment behind it. The sun is still there. The distance barely changes across those few inches. Yet the temperatures belong to different worlds. That should not happen according to ordinary experience. If you stand close to a furnace, the entire area feels hot. If you open an oven, heat rolls into the kitchen. If a pickup has been parked all afternoon in Phoenix, you do not need a physics degree to know that the steering wheel is planning revenge. Heat seems to spread through a place. It fills the air, reaches nearby objects, and makes everything join the same argument. Space does not work that way, because space is not a room. There is almost no air between Parker and the sun. There is almost no matter available to carry energy from the hot shield to the protected equipment. The shield receives the solar radiation. The instruments behind it do not. The sun cannot heat what its light cannot reach. The same principle controls the International Space Station. The station circles Earth about once every 90 minutes. During 24 hours, the crew passes through roughly 16 sunrises and 16 sunsets. The view is spectacular. The engineering problem is less poetic. One moment, sunlight strikes the outside of the station. A short time later, Earth blocks the sun. The illumination changes rapidly, but the entire station does not jump instantly from blazing heat to deep cold. Metal, equipment, water, air, and structural parts all store energy. They have thermal inertia. They heat and cool at different rates. A thin, exposed surface can respond quickly. A large module full of equipment responds more slowly. A tank of liquid has its own schedule. The station is not one object with one temperature. It is a collection of systems that constantly disagree about how warm they would like to be. On Earth, air helps settle that disagreement. Air touches warm surfaces, absorbs energy, moves, and shares that energy with cooler areas. Inside the station, engineers can use fans and circulating fluids because the cabin contains air. Outside, a fan would spin faithfully and accomplish almost nothing. There is no surrounding atmosphere to move. The station uses insulation, reflective coatings, pumps, pipes, heat exchangers, and large radiators. Internal systems collect excess energy from computers, equipment, and the crew. Fluid carries that energy to radiators. The radiators release it into space as infrared light. Space does not pull the heat out. The station must push the energy toward a surface that can radiate it away. This is the first part of the answer. The sun does not send hot air across 93 million miles. It sends radiation. We usually say that the sun is burning. It is not burning in the way wood, gasoline, or natural gas burns. Ordinary fire is a chemical reaction. A fuel reacts with another substance, usually oxygen, and releases energy. The sun is doing something much less domestic. Deep inside it, hydrogen nuclei are forced together by enormous pressure and temperature.
Thermal distortion.
They eventually combine into helium. A small amount of mass becomes energy. This process is nuclear fusion. The temperature at the center of the sun is about 27 million degrees Fahrenheit. The visible surface is cooler, at roughly 10,000 degrees Fahrenheit. Cooler is doing a lot of work in that sentence. Neither location has a comfortable patio season. Energy created near the center does not shoot directly into space. The solar interior is so dense that light is repeatedly absorbed and emitted. A photon may travel a short distance, collide with matter, change direction, and begin again. Its journey toward the surface can take thousands of years. Once light finally escapes, the final trip to Earth takes only about 8 minutes. The slowest part of the journey happens inside the sun. The fastest part happens across 93 million miles of space. During that final trip, the sunlight does not need air, wind, or any other material carrier. Electromagnetic radiation can travel through a vacuum. It keeps moving until something absorbs, reflects, or scatters it. That is why sunlight can cross the space between the sun and Earth without turning the path into a heated tunnel. Think about a flashlight in a dark garage.
Right there, in
the beam crosses the room and lands on the wall. If the air is clean, you barely see the path. Add dust or smoke, and the beam becomes visible because particles scatter some of the light. The wall receives the energy. Most of the empty path does not. The sun is a much larger flashlight. Earth is one of the walls. The confusion becomes worse because we use the words heat, cold, and temperature as though they were different labels for the same thing. They are not. Temperature describes the physical state of matter. In a simple picture, it is connected to the energy of the random motion of particles. In warmer matter, particles generally have more energy. In colder matter, they generally have less. Heat is energy moving from one system to another because of a temperature difference. Cold is not a substance that enters an object. When you touch something cold, energy leaves your skin and moves into the object. Your hand notices the loss and complains. This is why a metal seat at a Friday night football game can feel colder than the wooden bench beside it, even when both have been sitting outside for hours. The metal and wood may be close to the same temperature. Metal simply conducts energy away from your hand more quickly. Your skin is not reporting temperature alone. It is reporting the speed of energy transfer. The same mistake happens in summer. A metal truck bed and a wooden board can sit under the same Texas sun. The metal may feel far more aggressive because it transfers energy to your hand quickly. The hand does not run a laboratory. It runs an emergency warning system. In ordinary life, thermal energy moves in 3 main ways. The first is conduction. Energy passes through direct contact. A hot pan warms its handle. The handle warms a hand. The hand teaches a lesson that could have been learned with an oven mitt. The second is convection. Moving matter carries energy. Warm air rises, cooler air moves in. Water circulates inside a pot. A breeze removes the warm layer of air next to your skin. The third is radiation. Energy travels as electromagnetic waves. No contact is required. No air is required. Radiation is how sunlight reaches Earth. Conduction and convection become extremely weak in space because there is so little matter. Real space is not perfectly empty. It contains atoms, molecules, dust, charged particles, and plasma, but the density can be astonishingly low. At sea level, a small amount of air contains an enormous number of molecules. They collide constantly with one another and with every surface around them. In deep space, the same volume may contain only a few particles. In some regions, even fewer. Those particles can move very fast. Scientists may describe the gas as having a very high temperature. But high temperature does not automatically mean that the gas contains enough total energy to heat a spacecraft quickly. Imagine one person sprinting through an empty football stadium. He may be moving at record speed. The stadium is still not crowded. The solar corona provides a perfect example. The outer atmosphere of the sun reaches temperatures of millions of degrees, yet it is extremely thin. A spacecraft passing through it does not experience the same heating that it would experience inside dense air at the same temperature. The particles are energetic. There are simply not enough of them to transfer energy like a thick gas or liquid. This is why water at 180 degrees Fahrenheit is far more dangerous to your skin than air at 180 degrees. Water contains much more matter in the same volume and transfers energy much more effectively. A sauna can contain air hot enough to make the same temperature in water intolerable. The temperature number may match, the experience does not. Space takes that difference and pushes it to an extreme. This is also why an astronaut exposed to vacuum would not freeze instantly. Movies prefer a clear visual. The helmet breaks. The astronaut turns white, becomes a statue, and drifts away looking like a frozen store mannequin. Actual vacuum exposure begins with a different problem. Pressure. Earth's atmosphere presses on the human body all the time. We do not feel crushed because the pressure inside the body balances the pressure outside. Remove the external pressure and gases begin to expand. The boiling point of liquids also drops. At sea level, water boils at about 212 degrees Fahrenheit. At high elevation, lower air pressure allows it to boil at a lower temperature. In a near vacuum, water can boil at body temperature. This does not mean that all the blood inside a person instantly turns into steam. Blood remains inside vessels under internal pressure. But moisture on the tongue, eyes, and exposed tissues can begin to bubble and evaporate. In 1965, a technician named Jim LeBlanc was testing a pressure suit inside a vacuum chamber. A hose failed and the pressure dropped rapidly. Before he lost consciousness, LeBlanc remembered feeling the saliva on his tongue begin to boil. He was not hot. The pressure was gone. He remained conscious for only a few seconds because the brain was no longer receiving enough oxygen. The chamber was repressurized quickly, and he survived. He did not explode. Human skin is strong enough to contain the swelling of tissue. The body would expand, but it would not burst like a balloon. Holding the breath would make the situation worse. Air trapped in the lungs would expand and could tear delicate tissue. The correct response would be to exhale, although the opportunity to apply calm training in open space would be limited. An unprotected person would lose consciousness in roughly 10 to 15 seconds. Severe injury would follow if pressure and oxygen were not restored. Cooling would happen too, but it would not be the first event. The body would lose energy through radiation. Moisture would evaporate and carry energy away. Yet, there would be almost no surrounding matter to remove heat by conduction or convection. Cold water would cool a body faster than vacuum because water remains in contact with the skin and carries energy away efficiently. Vacuum does not attack with cold fingers. It removes the environment that normally returns energy. This distinction is so important that engineers reproduce it on Earth. In Sandusky, Ohio, the Neil Armstrong Test Facility contains one of the largest space environment chambers ever built. The chamber is about 100 feet across and 122 feet high, roughly the scale of the rotunda inside the United States Capitol. Entire spacecraft can fit inside. The chamber can create a powerful vacuum, but vacuum alone does not reproduce every thermal condition of space. Engineers must also control radiation, heating, and cooling. They build systems that shine energy on the spacecraft to imitate sunlight. They cool surrounding surfaces to imitate the dark background of space. They monitor how each component responds. The cold is not automatically produced by emptiness. It must be created through an energy balance. That is the part most simple explanations skip. The phrase "space is cold" makes it sound as though the vacuum is a giant freezer full of invisible cold air. There is no cold air. There is almost no air at all. An ideal vacuum does not have temperature in the same ordinary sense as a rock, a cup of coffee, or the atmosphere. Temperature normally describes matter. If there are no particles, there is nothing to average in the usual way. Real space contains some matter and a great deal of radiation. The thin gas can have a temperature. Radiation can also be described by a temperature. But an object placed in space has its own temperature. That temperature depends on how much energy the object receives, how much it reflects, how much it produces internally, and how much it radiates away. A dark surface usually absorbs more sunlight than a bright reflective surface. A thin sheet changes temperature faster than a thick block. Working electronics generate heat. A battery generates heat. A human generates heat. Point the same object toward the sun and it may become hot. Move it into shadow and it may cool. Cover it with a reflective layer and the balance changes again. Space does not assign a temperature to the object. The energy budget does. James Webb Space Telescope was built around this fact. Webb studies faint infrared radiation from distant galaxies, forming stars, clouds of dust, and planets around other stars. The trouble is that warm objects also emit infrared radiation. A warm telescope can blind itself. It is like trying to see a candle across a dark parking lot while someone shines high-beam headlights into your face. Webb therefore has a hot side and a cold side. The hot side contains the solar array, communications equipment, propulsion systems, and other hardware. It faces the sun, earth, and moon. The cold side carries the mirror and scientific instruments. It faces away from those major sources of heat. Between them is a 5-layer sun shield about the size of a tennis court. The shield does not work as one thick wall. The layers are separated so they do not touch. Direct contact would allow more conduction between them. The first layer receives the largest solar load. It reflects some energy and absorbs some. The absorbed energy is radiated toward the sides. The next layer receives less. Each layer repeats the process. By the time the energy reaches the cold side, the flow has been reduced dramatically. Across those 5 layers, the temperature difference can approach 570 degrees Fahrenheit. The hot side can reach about 185 degrees Fahrenheit. The cold side operates near minus 388 degrees. Both sides belong to the same machine. They are separated by a few yards, not by a planet. Nothing in everyday American weather comes close. A brutal summer day in Death Valley and a severe winter night in Alaska could not reproduce the full difference inside one telescope. One instrument needs even more help. The mid-infrared instrument, called MIRI, must operate near minus 448 degrees Fahrenheit. Passive cooling is not enough. A special cryocooler lowers its temperature to about 7 degrees above absolute zero. Webb is not cold because space placed it inside a freezer. It is cold because engineers blocked incoming radiation and designed the telescope to release its own energy. The vacuum helps by preventing air from carrying heat across the sun shield. But the energy still has to be moved and radiated. Nothing in space comes for free, not even cold. Now the famous number minus 455 degrees Fahrenheit becomes suspicious. People often call that the temperature of space. But if vacuum is not an ordinary material, what exactly has that temperature? The answer was first heard as annoying noise in New Jersey. In the 1960s, Arno Penzias and Robert Wilson were working with a large antenna at Bell Labs in Holmdel. The instrument picked up a weak microwave signal from every direction. They checked the equipment. They searched for local interference. They cleaned material left inside the antenna by pigeons. The pigeons were removed from the investigation. The signal remained. It was not coming from New York, military radar, or a broken component. It was coming from the entire sky. Penzias and Wilson had detected the cosmic microwave background, the oldest light that can travel freely through the universe. The early universe was hot and dense. Light could not move freely because it constantly interacted with charged particles. As the universe expanded, it cooled. Electrons combined with atomic nuclei. Neutral atoms formed. Light was finally able to travel long distances without being scattered every few inches. That ancient light is still moving through space. The universe has continued to expand for billions of years. As space expanded, the wavelengths of the light stretched. Longer wavelengths carry less energy. Today, that radiation has a temperature of about 2.7 degrees above absolute zero. That is roughly minus 455 degrees Fahrenheit. This is the number people mean when they say space is almost 455 degrees below zero. It is not the temperature of nothing. It is the temperature associated with ancient background radiation that fills the universe. A thermometer floating in space would not automatically read minus 455. Place it near Earth, and it may absorb direct sunlight. It may absorb sunlight reflected by clouds and oceans. It may receive infrared radiation from the planet. Its internal electronics may warm it. Place the same thermometer in shadow and the reading changes. Paint it black and the reading changes. Coat it with reflective material and the reading changes. The thermometer does not measure the reputation of space. It measures its own physical state. Far from stars, planets, and internal heat sources, an object would slowly radiate energy and approach an extremely low temperature. The cosmic background would eventually matter. Near the sun, the background radiation is almost irrelevant compared with the solar energy arriving every second. This explains why the moon can become both scorching and bitterly cold while remaining almost the same distance from the sun as Earth. The sunlight entering your kitchen window is nearly the same sunlight that strikes the lunar surface. The moon is only about 240,000 miles away. In astronomical terms, it is the house next door. Near the lunar equator, daytime temperatures can rise above 250 degrees Fahrenheit. At night, they can drop near minus 208 degrees.
Looks promising from here.
Inside some permanently shadowed craters near the poles, temperatures fall below minus 410 degrees Fahrenheit. No winter in Alaska approaches that. Those craters are among the coldest places in the solar system, and they are only a few days of travel from Earth. The sun is not weaker there. The moon simply has almost no atmosphere to store or redistribute energy. There are no oceans to absorb heat during the day and return it slowly at night. There are no winds carrying warm air toward cold regions. There are no clouds reflecting sunlight or slowing the escape of infrared energy. The lunar surface is covered by regolith, a layer of broken rock and dust created by billions of years of impacts. Regolith is a poor conductor of heat. The upper surface can become very hot, while material below remains much colder. When sunlight disappears, the surface continues to radiate energy into space. Almost nothing returns that energy. The moon does not cool because space touches it with something cold. It cools because it keeps spending energy after the income has stopped. The length of the lunar day makes the contrast worse. One full cycle of daylight and darkness lasts almost one Earth month. A point near the lunar equator spends roughly 2 weeks in sunlight and about 2 weeks in darkness. The ground has plenty of time to heat. Then it has plenty of time to cool. Earth rotates once in about 24 hours. Most places do not sit under sunlight for 2 straight weeks. Night arrives before the surface can behave like a lunar oven. After sunset, the atmosphere and oceans continue moving stored energy. The temperature drops, but the system does not begin from zero. On the moon, the surface is almost alone. Mars provides a different version of the problem. Mars has an atmosphere. It has clouds, winds, dust storms, and weather. The landscape can look strangely familiar in photographs, especially if you ignore the lack of breathable air, liquid water, trees, birds, gas stations, and every other useful feature. The atmosphere is mostly carbon dioxide, but it is very thin. Surface pressure is less than 1% of the average pressure on Earth. That is enough gas to move dust. It is not enough gas to store and transport energy the way the atmosphere of Earth does. The average surface temperature is around minus 80 degrees Fahrenheit. Some locations can become much warmer during the day. At night, temperatures fall sharply. Mars receives sunlight every day. It simply cannot manage that energy well. The planet was not always this cold and dry. Ancient channels, deltas, lake deposits, and water-formed minerals show that liquid water once moved across the surface. For that to happen over long periods, Mars needed different atmospheric conditions. Over time, the planet lost much of its atmosphere. Its lower gravity made gas easier to lose than on Earth. Ultraviolet radiation broke molecules apart in the upper atmosphere. The solar wind carried charged particles away. Mars lost the system that once allowed it to retain pressure and warmth. The MAVEN spacecraft spent more than 11 years studying the upper atmosphere of Mars and its interaction with the Sun. The mission ended in 2026 after the spacecraft was lost, but its data built a detailed picture of atmospheric escape. The Sun was not merely the heater in this story. Solar radiation and the solar wind helped strip away the atmosphere that Mars needed to hold heat. During intense solar activity, the rate of atmospheric loss could increase. The process did not happen in one dramatic afternoon. It continued over immense periods. Pressure fell. Surface water became unstable. Some water froze. Some became trapped inside minerals. Some molecules were broken apart, allowing light hydrogen to escape into space. Mars did not simply run out of sunlight, it lost the machinery that made sunlight useful. Venus shows the opposite failure. Venus is closer to the Sun, but distance alone does not explain its surface temperature near 870 degrees Fahrenheit. The atmosphere is extremely thick and consists mostly of carbon dioxide. Surface pressure is about 90 times the pressure on Earth. Standing there would not feel like standing under a heavy blanket. It would feel like placing the blanket under the weight of a deep ocean and then putting the entire arrangement inside an industrial oven. The clouds of Venus reflect a large amount of sunlight. That is why Venus appears so bright in the sky. Yet the energy that reaches the lower atmosphere and surface has great difficulty escaping. The hot surface emits infrared radiation. Carbon dioxide absorbs and emits infrared energy. Much of the radiation must work its way through the thick atmosphere before enough of it can finally leave for space. The result is a powerful greenhouse effect. Night provides almost no relief. The thick atmosphere moves energy so effectively that temperatures remain extreme across much of the planet. The moon keeps almost nothing. Venus holds far too much. Mars lost much of what it once had. Earth sits between them. Not because Earth occupies a magical address where the sun automatically produces mild afternoons. Distance matters, but it is only part of the system. Earth has an atmosphere dense enough to move and retain energy, but not as crushing as the atmosphere of Venus. It has oceans that absorb enormous amounts of heat. It rotates quickly enough to limit the length of day and night. It has clouds, ice, soil, vegetation, and moving air. The planet receives sunlight across the daytime side. Some energy is reflected by clouds, ice, and bright surfaces. The rest is absorbed by land, water, and atmosphere. Earth then emits energy back toward space as infrared radiation. If the planet absorbs more energy than it releases, it warms. If it releases more than it absorbs, it cools. Temperature changes until a new balance forms. The atmosphere does not create energy. It changes how quickly energy moves and escapes. Certain gases absorb infrared radiation leaving the surface. They emit that energy again. Some travels upward, some returns downward. This process keeps the surface warmer than it would be without an atmosphere. Calling the atmosphere a blanket is useful, but incomplete. A blanket reduces heat loss from a body that already produces energy. The atmosphere also moves. It carries water vapor, forms clouds, creates storms, and transports energy from warm regions toward colder ones. The oceans perform an even larger storage job. Water can absorb a great deal of energy without changing temperature quickly. During the day in summer, oceans store heat. At night and during winter, they release it gradually. This is why coastal climates often have smaller temperature swings than the interior of a continent. The ocean acts like an enormous thermal battery. Clouds play both sides. During the day, clouds can reflect sunlight and reduce heating. At night, they can absorb infrared radiation from the surface and slow cooling. A clear winter night often becomes colder than a cloudy night because more energy escapes directly toward space. Snow and ice reflect sunlight efficiently. Dark soil and ocean water absorb more. When ice cover changes, the planetary energy balance changes with it. Earth is constantly performing this accounting without a control room. The atmosphere itself looks enormous from the ground. The sky appears deep and endless. Aircraft climb for miles. Storm clouds tower above cities. Seen from space, the useful atmosphere becomes a thin blue line. There is no sharp wall where air suddenly stops. The atmosphere becomes thinner with altitude and gradually blends into the space environment. The commonly used boundary near 62 miles is a convention, not a glass ceiling. Most of the atmospheric mass lies much closer to the surface. Scale Earth down to the size of an apple, and the layer containing almost all weather, air, clouds, and human life becomes thinner than the skin. That nearly invisible layer separates an ordinary afternoon in Ohio from the thermal swings of the moon.
Fine now.
The atmosphere is not working alone. Earth
morning.
gravity helps retain gases. The magnetic field changes how charged particles from the solar wind interact with the planet. The oceans store energy. Geological processes move carbon between the atmosphere, rocks, oceans, and interior. Living organisms alter atmospheric chemistry. Earth is not a rock under a blanket, it is a working system. The difference is easy to see without leaving the United States. A black pickup in Arizona can become dangerously hot under sunlight. A white truck beside it absorbs less visible solar energy. The asphalt below may become hotter than the air. Grass remains cooler because water evaporating from plants carries energy away. Everything sits under the same sun. Everything reaches a different temperature. The sun did not send different rays to the truck, road, and grass. The materials handled the energy differently. A closed car demonstrates another part of the mechanism. Sunlight enters through the windows and heats the seats, dashboard, and floor. Those surfaces warm the air. The hot air cannot mix efficiently with cooler outside air. Energy accumulates and the temperature rises. The interior of a car is not a perfect model of the greenhouse effect on a planet, but it proves a basic point. Receiving sunlight and losing heat are different processes. A vacuum-insulated bottle proves the opposite point. The space between its walls reduces conduction and convection. Reflective surfaces reduce radiation. The lid limits the movement of air. The bottle does not heat the coffee. It prevents the coffee from losing energy quickly. It is a small spacecraft for caffeine. A spacesuit must solve a more complicated version of the same problem. The suit provides pressure and oxygen, but it must also remove heat. The human body continuously produces energy. Muscles work, equipment operates. Sunlight may heat the outside of the suit. Without a cooling system, an astronaut can overheat in the cold of space. Water circulates through small tubes in a garment worn under the suit. The water collects heat from the body. The life support system then moves that energy away. This sounds backward only because the phrase cold space has already created the wrong picture. Space is not one giant cold environment. It is an environment where energy does not move the way it does inside an atmosphere. A hot object may remain hot because there is no air to carry heat away. A shaded object may become extremely cold because nothing replaces the energy it continues to radiate. A human may overheat in sunlight and freeze much later in darkness. The same vacuum permits both. Material choice becomes critical. Engineers study how well a surface absorbs sunlight and how well it emits infrared radiation. Those two properties are not always the same. A coating can reflect much of the incoming sunlight while still releasing internal heat efficiently. That is ideal for many spacecraft surfaces. Another coating may look almost identical to the human eye, but behave very differently in infrared wavelengths. To a casual observer, two white panels look the same. To a thermal engineer, one keeps a spacecraft alive and the other produces a very expensive investigation. This is why spacecraft wear reflective blankets, bright panels, dark radiators, and carefully selected coatings. It may look as though someone wrapped part of the vehicle in kitchen foil. That kitchen foil may be the difference between functioning electronics and a dead satellite. Parker Solar Probe carries the principle to the most extreme location humans have reached. Its shield faces the sun. The spacecraft must keep that shield pointed correctly. If the instruments moved into direct sunlight during the closest approach, the protection would fail quickly. Parker therefore operates with a high degree of autonomy. During the most intense part of the encounter, mission controllers in Maryland cannot simply steer it moment by moment like a remote control airplane. The spacecraft senses its orientation and corrects itself. A few inches of shield and a precise direction separate functioning science instruments from solar destruction. James Webb uses a similar idea for the opposite purpose. Parker survives extreme incoming energy. Webb creates extreme cold so it can detect faint infrared light. One flies close to the sun, the other hides from it. Both depend on controlling which surfaces see the sun and which surfaces see dark space. The real story is not hot sun against cold universe. The real story is exposure. A surface facing the sun receives energy. A surface hidden from it does not. A material that absorbs radiation heats differently from one that reflects it. A body that emits energy efficiently cools faster than one that does not. The location matters. The design matters more than intuition expects. This is also the answer to the original contradiction. Why can one side of a spacecraft become extremely hot while instruments a few inches behind the shield remain near room temperature? Because radiation travels in straight lines until matter redirects or absorbs it. The shield intercepts the solar energy. Almost no air exists to move that heat around the shield. The protected equipment receives far less energy and remains cooler. Why does sunlight cross space without heating the path? Because the path contains very little matter. Light carries energy through the vacuum, but almost nothing is available to absorb that energy until the light reaches an object. Why does an astronaut not freeze instantly? Because rapid freezing requires rapid energy transfer. Vacuum provides almost no conduction or convection. Pressure loss and oxygen deprivation become critical long before the body has time to turn into ice. Why do scientists describe deep space as nearly -455 degrees Fahrenheit? Because the universe is filled with weak microwave radiation left from the early universe. That radiation corresponds to about 2.7 degrees above absolute zero. Why does the moon swing between an oven and a freezer? Because it has almost no atmosphere or ocean to store and redistribute energy. Why is Mars cold despite receiving sunlight every day? Because a thin atmosphere cannot maintain the climate the planet once had, and much of the earlier atmosphere escaped to space. Why is Venus so hot? Because its massive carbon dioxide atmosphere makes it difficult for absorbed energy to escape. Why is Earth different? Because Earth can receive, store, move, and release energy at rates that keep liquid oceans and a broad range of habitable temperatures. That balance is not a permanent gift. The sun changes. Its activity rises and falls. Solar storms strike the planets. Over immense periods, the brightness of the sun slowly increases. Earth also changes. Atmospheric composition changes. Ice expands and retreats. Continents move. Oceans circulate differently. Life alters the chemistry of the air and water. What feels permanent during a human lifetime is a moving arrangement on geological time. The planet has survived asteroid impacts, massive volcanic episodes, ice ages, and major shifts in climate. Survival of the planet does not guarantee preservation of conditions comfortable for humans. Earth can continue without offering us good weather. That is why the atmosphere should not be imagined as a thick, permanent wall. It is a dynamic part of a larger system. Change its composition and the rate of energy loss changes. Change ice cover and reflection changes. Change ocean circulation and heat moves differently. The energy keeps arriving from the sun either way. On an ordinary evening, the system hides its complexity. The sun drops below the horizon. The ground releases energy it absorbed during the day. Buildings and roads cool. Air moves. Water in soil and plants evaporates. Clouds absorb and emit infrared radiation. Oceans continue returning energy stored hours, months, and even years earlier. Night is not the absence of solar energy. It is the next stage of what the planet did with the sunlight. On the moon, the same sunset begins a long withdrawal. The surface spends energy and receives almost nothing for about 2 weeks. On Mars, the thin atmosphere offers limited help. On Venus, the dense atmosphere refuses to let the surface cool much at all. On Earth, sunset becomes an ordinary evening because several systems continue working after direct sunlight disappears. Every home repeats a smaller version of the same physics. Sunlight enters a kitchen window and lands on the floor. The floor absorbs energy and warms. Air touching the floor gains energy and rises. Furniture and walls store some of it. Later, the house emits infrared radiation and loses heat through windows, walls, and ventilation. A ray that crossed 93 million miles of vacuum finishes its trip under the dining table. When sunlight warms your face, hot air has not traveled from the sun. Electromagnetic radiation has crossed almost empty space and deposited energy in your skin. Move into the shade and the direct solar radiation stops. The surrounding air may be nearly the same temperature, yet the difference is immediate. On Earth, air, ground, and nearby objects continue sharing energy, so the shade does not become a cryogenic chamber. In space, the difference between sunlight and shadow appears with fewer intermediaries. The sun does not heat space like a furnace heating a house. It sends energy through space. Vacuum does not freeze objects like ice water. It gives them almost nothing in return while they radiate energy away. Temperature belongs to the object and its energy balance. This single rule connects Parker's solar probe, James Webb, the International Space Station, a moon crater, the atmosphere of Mars, the clouds of Venus, a truck in Phoenix, and a cup of coffee inside a vacuum bottle. Only the scale changes. From the ground, the atmosphere feels limitless. From outside, it is a blue film pressed against a rock moving through near vacuum. Inside that film, sunlight becomes wind, rain, cloud, ocean current, summer heat, winter cold, and an ordinary evening. Above it, a spacecraft can experience extreme heat and deep cold across a distance shorter than a living room. We do not live in a warm region of the universe that was prepared for us. Earth travels through the same space as the Moon and Mars. It receives radiation from the same sun. What makes this planet different is what happens after the energy arrives. Earth reflects some, it absorbs some, it stores some, it moves some. It releases the rest. Not too quickly, not too slowly. The balance is active every second. The sun keeps sending energy. The surface keeps absorbing it. The atmosphere and oceans keep moving it. The planet keeps radiating it back into space. An ordinary afternoon is not a passive condition. It is a process that has not stopped. Parker Solar Probe demonstrates the rule a few million miles above the solar surface. Its shield faces temperatures that could destroy the spacecraft. A few inches behind the shield, the instruments remain near room temperature. The same sun is on both sides. The difference is what the light can reach. Earth does not escape the physics of space. Earth manages it. That is why the same sunlight can bake the moon, shine over frozen rivers on Mars, help keep Venus near 870 degrees, and pass through your kitchen window without ending the afternoon. The sun provides the energy. The planet decides what happens next.